Hello, and welcome to this introduction to design of experiment, in short DoE. We're going to take a look today at the example of a robustness evaluation of an HPLC method based on the substance of norfloxacin. But before we start, we need to consider some terminology first. We need to understand that there is a response. The response is a parameter of which the robustness is evaluated. Sometimes it's also known as the response variable, and in our case it's going to be the retention time. Additionally, we need to understand that there are factors. These are the controllable input parameters that influence our response. In our example we have three of them, namely the pH value, the additive concentration, and the column temperature. Lastly, we need to consider that factors do have levels. These are now the actual numeric values of the factors which represent the region in which the robustness of the response is evaluated. But with this now out of the way, we can go and define our factors more closely. First of all, as I mentioned before, we are going to take a look at three factors: pH value, additive concentration, and column temperature. How these factors came to be is mainly through brainstorming and previous experience. The same thing applies also for the factor levels, and these are extremely important to choose right, because if you think about choosing them in a quite wide range, then it's highly likely that your method won't be robust with these changes. The same applies in a different way if you choose them too narrow. Then the method will always be robust because the changes are way too slight. Meaning that optimally you need to consider what are reasonable mistakes that can happen during, for example, eluent preparation, and based on these thoughts you can generate the factor levels of the experiments. But now let's consider the table below. First of all, we see that our three factors also have a coded value. This is done for more easier understanding of the tables later, because this makes them more easier to read. Additionally, we also see that our factors have optimal values. These optimal values have been previously determined in the method development and method optimization part. And additionally, we think that these factors actually influence the response, the retention time. But now, with this knowledge, we can go and start to look in our designs that we are going to use. In our case, we are using a normal full factorial design. This design is based on the following formula: n equals 2 to the power of k, where n is representative for the performed experiments that we're going to need. 2 represents the factor levels. In our case, this design only uses 2 levels, plus and minus, and k, which are the numbers of factors. That means, for our example, we need in total 8 experiments, because we have 3 factors and 2 factor levels. So, now let's consider how such a table might look like. We see that we have our 8 experiments, and those levels now are here in the coded manner, meaning that plus means level above the optimal value and minus represents a value below the optimal value. We start to fill this table now in a way that only one combination of plus and minus for every experiment is created in the following manner. And with this systematic approach, we were able to get way more information from a design of experimental point of view if we compare it to the one factor at a time approach, where we only change, as the name suggests, one factor in each experiment. However, in design of experiment, we change multiple factors in one experimental run. And why this is beneficial will become evident later on. Now we're going to look at the same table again, just in a decoded way, meaning then instead of having pluses and minuses here, we actually see what those values mean. And we see that from the optimal value we have gone up 0.2 pH units up and down. The same thing applies for the additive concentration, and the column temperature has been varied plus minus 1 degree. Now we nearly can start performing our experiments and determining the retention time of norfloxacin, but we need to consider one more thing, and that's the actual order of measurement. The reason for this is that we can't be sure that there are any other factors which are influential to the retention time and that we just have forgotten or have no control over. And to minimize their effect on the retention time, we randomize our experimental order. This is the reason why this blue column has been implemented here. Now with this knowledge, we can go on and start to perform our experiments and also determine the retention time of norfloxacin with these different runs. And from here on, we are now starting to go into the calculation part of design of experiment. We are now able to calculate factors, which are representative here. For example, factor A equals the pH value, the effect on the retention time. This is calculated in the following way. We add up all the retention times of positive factor levels, divide them by 4, and then we also sum up all the retention times from levels which have a negative sign and divide them by 4 and subtract them from the previous value. This now gives us the value of minus 1.48 and is representative of the effect of the pH value on our retention time. The same rule applies also for calculating the effect B of additive concentration and C, the column temperature. To maybe make this easier understandable, we can also visualize this in the following plot, where we plot the factors at low level against the factors and the factors at high level against the actual effect size. And the result is going to be exactly the same. A steep slope is representative for a larger impact than not a steep slope. Now, we also have to consider that these numeric values are only valid in the region we have chosen. So this minus 1.48 is only valid in between plus minus 0.2 units of pH up and down, and the same applies for factor B and C. But just by looking at this now, we could assume that the pH value has the highest impact on our response to retention time. And it looks like the column temperature and additive concentration do not really impact the retention time of norfloxacin that much. But we need to consider something else first, which shows right now what design of experiment is capable of. And that's the so-called interactions. Because the following or the previous result we could have also just gotten from a one factor at a time approach. But what we can now do is we can monitor an additional effect, and that's the, for example, interaction of the pH value and additive concentration. To do this, we expand our table now, and this is done in the quite simple manner of multiplication of factor levels. In our case, we multiply, for example, the factor A and B, and the resulting sign is going to be one part of the interaction, meaning that if we multiply with plus and plus sign, we get a positive sign, and plus and minus sign is going to be negative. I think you understand how this goes. And from here on, we get a whole new part of the table. This is an interaction table now. And we don't have to perform any more experiments for this. All of this information has been performed by our 8 experimental runs, which has been done previously. We just need to calculate the interactions again. And these are now all interactions possible between the factors and also 3 times interactions between all factors in total. Now this can also be calculated into numeric values, which you see down below, which is exactly the same formula applied previously to the normal effects. And with this now, we see that in fact not only the pH value seems to have quite a significant influence, also the interaction between pH value and additive concentration seems to have quite a significant effect on our response. And this is something that we can only see with the application of design of experiment, and would not be possible if we would just have used the one factor at a time approach. That's one of the real benefits of design of experiment. To make this perhaps a bit more clear, let's try to visualize this again. Here we plotted one factor A on the x-axis with low level and high level values, and we kept factor B at +1. And we can see that there is a slight slope. If we, however, now plot all the values from -1, the levels, against it, then we see that the slope tilts quite strongly. And this is an evidence that there is a strong interaction between factor A and B. Another way to look at this might be with these contour plots. Here we plotted two different factors against each other, namely the column temperature and the pH value. But before we go deeper into this, I would like to explain you those black dots around, which are representative for our design region that we have used. So all our robustness evaluations are only valid in these regions. And how these plots work now is that if we look at the tilt of the lines, we can estimate how strong those two effects interact. In this case, the tilting of the line is quite weak, so we can assume that there is not that strong of an effect between column temperature and pH value. However, we can see the lower we go with the pH value, and also the lower we go with the temperature, the stronger these interactions become. It is going to become even more evident if we take a look at the next example, which is again the additive concentration plotted against the pH value, and here we see that the lines are quite strongly tilted, implying that here is a strong interaction which is quite influential on our response. But to sum this now up, we have learned now that the retention time of norfloxacin is not robust towards the changes of pH value between 9.4 and 9.8. This has become clear from our only looking at the main effects. From this table at the start, it also looked like that the additive concentration between 4.8 and 5.2 millimoles had no real influence on the retention time. However, as we expanded our table and looked at the interactions, we've seen in fact that when the pH value and additive concentration interact, we have quite a strong effect on the retention time, which we would normally have not seen if we wouldn't have applied design of experiment. Lastly, we have seen that the other factors and interactions like column temperature, the interactions of column temperature with pH, for example, do not influence the retention time of norfloxacin in a significant way. Lastly, I would like to note that normally in the design of experiment approach, you would apply statistical tools as ANOVA to determine p-values to really be sure that you have significant effects. We have used now only subjective methods to do so. But regarding that this course is going to be an introduction, we decided not to include these techniques here. I still hope that you have learned something new about design of experiment and maybe also thinking about applying it for your next robustness evaluation. So, thank you very much for your attention.